ASML started looking at another material, tin. Now, tin has a much higher emission peak, around 13.5 nanometers, which results in a 5 to 10 times higher conversion efficiency than xenon. But just like xenon, neutral tin atoms also absorb EUV light. So they came up with a crazy idea: to shoot one tiny tin droplet at a time. But to get the required power, you would have to make and hit thousands of droplets every second, all of which have to be the exact same shape and size. But it turns out that you can't instantly make thousands of tin droplets that are the exact same. So they found a workaround. To make the droplets, extremely pure tin is melted and pushed through a microscopic nozzle by high-pressure nitrogen. This nozzle vibrates at a high frequency, breaking the stream into tiny droplets. These droplets are irregular in size, shape, velocity, and distance, and the whole process is chaotic.
That's like our magic sauce, is how do you modulate that tin jet so that it forms the droplets we want and that they're stable.
I think we found some paper that described this process, and it was sort of eye-opening to me that it seems like all the droplets actually come out irregular out of the nozzle. But then before they reach the side where they get hit by the laser, like the little irregular droplets come together to form these perfectly spaced, perfectly regular droplets that are about the same size and shape, and all traveling at the same velocity. That feels like magic to me, Jason.
Yeah, it's exactly that. It's how do you take a long stream of a tin jet that wants to break up into all these irregular droplets and like force onto it that it's going to collapse into a single droplet and then happen again and again and again.
You also don't have that many variables to play with. So you've got the pressure with which you push out the tin, and the frequency of the nozzle. Yeah, it seems like a hard problem to solve.
There's not a whole lot of variables to play with, and so mastering that modulation of the jet is how we make the droplets.
But these droplets not only have to be identical, they have to be moving incredibly fast.
What will happen is if the next droplet that's coming down the line is too close, then it'll actually get like disturbed and mess up the next plasma event. So we have a requirement, which is both that we make 50,000 droplets per second, but also that they're traveling extremely fast.
By 2011, their laser-produced plasma source reached 11 watts, which was more than double what they managed with their previous source. But they were still limited to just 5 wafers per hour. So they needed to increase the power, and fast, because they promised they'd hit 60 wafers per hour by the end of 2011. Unfortunately, this new method had a major flaw.
Now the problem with the tin is you hit a droplet, you generate EUV with a very decent conversion efficiency. Where does the tin go? Because like, 30 centimeters away, you have this atomically flat, very beautiful, very expensive mirror from our friends at Zeiss. And in the early days, we would coat the thing within like this.
These machines need to run for a year. You're putting liters of tin through this plasma event, and a single nanometer of tin, if it was to land on that collector mirror, you'd have to take the collector out of commission. We need to keep it almost perfectly clean for a year.
Yeah, how do you even approach that?
So our main tool here is the hydrogen gas, actually.
They filled the chamber with low-pressure hydrogen. This slows and cools the tin particles down, and even if some tin makes it to the collector, the hydrogen pulls it off to form a gas called stenane. This way, the machine cleans the collectors while it's running. But that hydrogen gas also gets hot from all those tin explosions. So they need to keep flushing new, cooler hydrogen into the system while flushing out the stenane and hotter gas. But they had to get the pressure and the flow rate just right. I mean, too little hydrogen and the mirrors would get too dirty, but too much hydrogen would not only absorb too much EUV light, but it would also cause the system to overheat.
But the question is, how much heat is there? How much energy is being deposited into the gas? And we were stumped for quite some time. If you look at an EUV light source, what you'll see is that it's kind of like a globe of like purplish red light. And you kind of ask yourself, like, why is that happening? So we bought an ultra-fast camera. What we realized is that after every plasma event, there's a shock wave that goes propagating out into the hydrogen gas. And it's extremely repeatable. And you think to yourself, there must be like an explanation for this. And there's this formula, the Taylor von Neumann-Zidov formula that explains point source explosions in an environment, and like say a nuclear blast out to like supernova.